Good afternoon, everybody. Thank you guys for being here. It's a pleasure to be back here in Abu Dhabi and see so many people in the audience here in person, even during Ramadan. Thank you, Nell and Andrew, and all those involved for staying late during Ramadan. This is a special occasion because we have a very renowned scientist who's here in person, who's visiting us for a few days, Professor Ashley Montanaro from the University of Bristol. He's really one of those big names in quantum algorithms and quantum computational complexity. He has written many papers on the topic. He's also a co-founder of a quantum algorithm startup in the UK called Phasecraft. And well, what else to say? Professor of quantum computation in the University of Bristol. He's also a grantee of the European Research Council, and he's also received the Whitehead Prize by the London Mathematical Society. So it's really a pleasure to have him here. He kindly accepted my invitation even without knowing me personally. So it's really generous from him to be here for so many days and have the chance to discuss with him. It's really a pleasure to have you, Ashley. Thank you for your time, and please go ahead. Thanks.
Great. Well, yes. Well, thanks firstly so much for that very kind introduction, Leandro, and for the invitation to visit here. And thanks to you all for coming to my talk today. I very much hope I'll get a chance to talk to many of you over the course of this week. And as Leandro said, I mean, please do interrupt at any point during my talk. I'm very happy to have a discussion at any time. So, as Leandro mentioned, I have these kind of two hats as co-founder of Phasecraft and also working at the University of Bristol. And today what I'd like to talk about is some work that was done at Phasecraft on near-term quantum algorithms, near-term quantum computing. And this is joint work, firstly with some of the other team at Phasecraft, Yannick Esposo, who's a PhD student working with us, Filippo Gambetta, Raul Santos, and Sergio Sanchez. And also with some of the team at Google, Wojtek, Tom, and Eric, who have been helping us out with our experiments there. And everything I'm going to say is based on this paper, which is on the archive and read it there. Okay, so the title of this talk is very long, but I guess the background is maybe a bit shorter to say. So basically, this is a talk about quantum simulation or algorithms for quantum simulation. So one of the most exciting, I guess I would say, potential applications of quantum computers is simulating physical systems that might be too difficult to simulate using our best classical methods. This in particular might apply to physical systems where quantum mechanics plays an important role. And I guess it's very natural to think that quantum computers could have an advantage here, because to represent the quantum state of a system that has n particles and atoms or something like this takes scaling takes scaling that's exponential at n classically, whereas on a quantum computer we can somehow represent the quantum system natively using maybe around n qubits or something like this. So it's kind of very natural to think we might be able to see a quantum speedup here. And this is a sort of very exciting thing because there are a number of really important problems which we would really like to solve, and yet we're very much struggling to do so using our classical methods. And this includes developing new batteries, high-performance batteries, high-performance solar cells, maybe particularly of interest around here, and even maybe developing something like a high-temperature superconductor that's more suitable for use in making low-loss power lines or something like this. Or basically any sort of innovation in material systems where we expect that quantum mechanics is going to play a key role. So many people think that quantum computers will be very useful for simulating quantum systems, but somehow making this into a real thing, making this into a real-world quantum speedup takes quite a lot of work. Firstly, you need to find an efficient quantum algorithm, and you need to perhaps take the sort of textbook quantum algorithms for quantum simulation, which maybe have complexity which is not fully optimized. You need to sort of optimize this quite finely. And then ultimately, you need to implement this quantum algorithm on a real quantum device and sort of demonstrate some kind of physically meaningful results. And basically what this talk is about is some experimental work that we did together with the team at Google, which is implementing a particular quantum simulation algorithm on their quantum hardware and seeing how well it performed. And the quantum algorithm that we were looking at was trying to produce the ground state of the so-called Fermi-Hubbard model. Now, this may not be so familiar to everyone here, certainly it was not to me when I started thinking about this a few years ago as a computer scientist. So I'll just sort of say a few words about this before we get on to the results, but please do ask any questions if there's anything. So basically, the Fermi-Hubbard model is a highly simplified model of the behavior of some strongly correlated electronic system. So we imagine that we have some electrons and they're hopping around within some kind of lattice of atoms, and they can interact when they're on the same sites, and they can't interact when they're not on the same site. So this is this sort of picture on the left-hand side where we've got this sort of 4x4 lattice of atoms, and we've got some electrons that are on some of these sites. So we can have either a spin down electron or a spin up electron, or we can have both or none. And these things are moving around, and when they're on the same site, they can interact with each other. And although this is an incredibly simple model, it's still very hard to solve classically. And I guess it's fair to say it's a grand challenge of condensed matter physics to solve this model. And yet, because it's so heavily simplified and easy to somehow write down, quite a few people think it might be a plausible target for quantum computers to solve in this near-term sort of NIS era. And as well as being scientifically interesting in itself, that's interesting because it's sort of on this pathway to physically relevant, like real-world material systems. Because if you understand the Fermi-Hubbard model, you're probably already understanding some of the complexity that goes into much more realistic systems that might help you develop high-temperature superconductors or something like this. So, okay, so basically the task that we're thinking about with this problem is producing the ground state of a particular quantum system, a particular quantum Hamiltonian, H, and this is the way it's defined. So we have some hopping terms here, and some called on-site terms here. And these are all described in terms of fermionic operators. So for those who haven't seen these before, I mean, maybe don't worry about them too much. I'll just sort of say intuitively what they mean. What this is saying is that this term involves a fermi or an electron hopping between site I and site J. So this sigma is a spin, so it could be spin up or spin down. And this is saying that this is an annihilation operator here. This is saying we're going to delete or annihilate an electron with spin sigma at site J. And this is saying we're going to create an electron with spin sigma at site I. And these I and J should be adjacent in the lattice. And then you've got the mission conjugate here as well, so make this a mission operator. So this is basically saying this term moves an electron between site I and site J. And then we've got this one here, and these are fermionic number operators. And this is basically saying interacts the electron that's spin up at site K, if there is one, with the electron that's spin down at site K. And this is sum over all of the sites. So you can sort of think of this as giving us an energy penalty when we have two electrons at the same site. And we've got some kind of constants in front that set the overall scaling of these terms. And there's a t here, and in fact, it's always going to be 1 for the purpose of the talk. And there's this u here. And then as this u changes, this changes the behavior of this quantum system. And what we want to do is find the lowest energy state of this Hamiltonian H. So we want to, ultimately, this H we can represent as some really big matrix, an exponentially big matrix, and we wanted to find the eigenvector of that matrix that has the lowest eigenvalue. And that's what we wanted to do. And in the case of a quantum algorithm, we wanted to produce this state on a quantum computer. And then we can do some measurements on it to try to understand something about its physical properties. So, as I mentioned, if you want to represent this thing exactly, this ground state on a classical computer, the scaling of this is going to be exponential in the size of the lattice. In fact, it's going to be 2 to twice the number of sites in the lattice, because basically we can think of this thing as being represented by, if you have L sites, it's represented by 2L qubits, because we have a qubit for spin up and a qubit for spin down at each site, and we have a 0 or a 1 according to whether there's an electron or not at that site with that spin. So this is very challenging to even write down classically. And in fact, the largest case that I'm aware of where someone solved this model exactly was just 22 sites, 22 atoms. And this was back in 2005, so it's a long time ago now. But this needed 7 terabytes of memory, and if you wanted to go to larger sizes, then you would need even larger amounts of memory. So that's the exact solution. On the other hand, you could try to solve this model approximately, and you could go to much larger sizes then. But unfortunately, then you might pay a penalty in terms of accuracy. And there's a very nice comprehensive comparison of different algorithms for solving the Hubbard model, different classical algorithms for solving the Hubbard model from 2015. And in some cases, even though these algorithms are very heavily developed over many years and with a lot of hard work, in many cases, there's still a gap, which is larger than we would like, between the estimates that these different algorithms produce for certain quantities, like, for example, the energy, the ground state energy. So, because these algorithms generally don't come with guarantees, it's actually hard to know exactly what the ground energy is for particular, well, in the limit or even for particular instances that we might care about. So, somehow this is very hard classically, and that leaves us with some hope that we might get a quantum advantage for solving this problem. And that's what this talk's going to be about, trying to solve Fermi-Hubbard and find a quantum advantage from that. I should spoil the surprise by saying, the sizes we're going to look at, we're not going to find a quantum advantage in this talk, but at least it's maybe pointing towards the future. And yeah, first we should look at some previous experiments. So there are a few people have experimentally tried to solve instances of the Fermi-Hubbard model on a quantum computer. There are also many sort of analog quantum simulation experiments, which are much larger, I should say, that people have done. So I'm only focusing on the ones which are implemented on universal quantum computers here. And back in 2018, on an ion trap, a team managed to solve a 1×2 instance. This is sort of the smallest non-trivial instance of the Fermi-Hubbard model on an ion trap. We looked at also a 1×2 instance on superconducting qubit hardware, and more recently, a team from IBM managed to solve a 4-site Fermi-Hubbard instance. And one thing you might notice is that the number of qubits that's used here for these different instances is smaller than the number I just said, of twice the number of sites. And the reason is that in each of these cases, the authors used some kind of compression technique to restrict to some kind of subspace and solve the model within that subspace. So that reduces the number of qubits you need. But the penalty that you pay is that as you increase the size of the system you're looking at, the quantum circuits get more and more complex, and it's harder to see how you would implement them. It might still be in principle efficient, but in practice, you need quite a lot of gates, and it's not necessarily suitable for a near-term. Also, I should say as well, there's some more recent work by the Google AI quantum team on time dynamics of the Fermi-Hubbard model, which went to larger sizes. I think it was 16 qubits. It's a very nice paper as well. And back in 2019, I guess, we did some work, which I guess I just mentioned in a meeting, about trying to look at classical numerics for understanding how well quantum algorithms could perform for finding the ground state of the Fermi-Hubbard model based on this variational method, or D3. And what we estimated from this work is that if we were looking for the ground state of a 5×5 Fermi-Hubbard instance, so this is bigger than people are able to solve exactly classically, if we were wanting to do this with a quantum algorithm, we might be able to do it based on extrapolating the results we had, using a quantum circuit that has depth of the order of 300 to 500, something like that. So this is a lot smaller than a lot of other applications of quantum computers, but it's still beyond this sort of NISQ era of quantum computing. And one thing we were interested in this work is, can we try to think of ways in which we could learn about the physics of the Fermi-Hubbard model, especially the low energy states of the Fermi-Hubbard model, with quantum circuits that are much shallower than this, that are somehow closer to ones we could do in the NISQ era. Can we sort of think of maybe more qualitative physical questions that we can ask about the model, which we can answer using nearer term circuits? And can we implement these and see if they actually work in practice?
Actually, I have a question.
Sure.
Perhaps you will touch upon this, but so here, I have a question. Perhaps you will touch upon this, but let me ask you already. So when you say 5×5 instance, you refer to the number of lattices, right? 5×5. But
yes.
So this is the Hamiltonian in terms of fermionic annihilation and creation operators. And then you have to map it to qubits, right? To qubit operators. So this would be another number, right? This
yes, this would be 50. But the number would be 50 for at least the mappings that we're thinking about.
I see. And that's why it becomes unsolvable classically with current.
Exactly. Okay. And the reason that this number is is less than 2 times the sizes that you can think of sort of subspaces that, for example, a natural thing is to restrict to a particular fermionic occupation number, which is like Hamming weight, the number of electrons in the system. And then the number of qubits you need is the log of the dimension of the largest one of these subspaces. And for small sizes, this can be substantially smaller than the overall space, but as the size increases, actually you save less and less with this kind of check. Okay, so what did we do? Well, as I said, we did an experiment to try to find ground states of Fermi-Hubbard using a quantum computer. And I guess, you know, for a theorist, I guess, the key messages from the work are that, firstly, if you have a much lower depth variational quantum circuit, you might still be able to get some qualitative physical insights about the Fermi-Hubbard model. This is before you get to the regime where you're very precisely approximating the ground state. And also that, you know, it's possible to produce, to run an algorithm on the quantum computer, which doesn't use these kind of compression tricks and is more easily scalable. So it's easy to see that how as quantum hardware improves, you would just scale up this algorithm. And the sort of instances we were looking at looked like this. So we were looking at instances on up to 8 sites. So this is up to 16 qubits. And the number of gates we were using is of, you know, the order of 150, 170 sort of gates. So this is, I guess, you know, a factor of 10 more than the previous work. And also, yeah, I mean, this variational layers here might be interesting to keep it here as well. Basically, the variational circuits we were looking at, you know, you're optimizing over a family of circuits that have some particular form, and then naturally divided up into layers of the particular circuit family we were looking at. And we were able to go up to 2 variational layers for a 1×4 instance, but only 1 variational layer for these instances. And you know, I should stress this doesn't mean that the quantum circuit itself is depth 1. I mean, that the depth ends up being a bit higher. And I'll say a bit more in a minute about what these circuits actually look like.
Sorry, very primitive question. Can you define again those 2 quantum? In your, yeah, exactly. Could you define again what the variational layer is? And
Oh, sure. I'll do that in a minute. I think
okay,
it'll be easier in a minute. Yeah, I'll say what the circuits look like, and then you may have to wait a couple of minutes, but it'll be okay. So what I want to do next is explain how the experiment works, what the different steps were we have to go through, and basically for these sorts of experiments, there are always some steps you need to follow. First, you need to even write down the Hamiltonian that you want to solve in such a way that you can put it on your quantum computer. You have to write it down in terms of qubits as opposed to fermionic operators. Then you need to define the family of circuits that you want to use to find the ground state of this system. Then you need to figure out how you're going to optimize over that family of circuits. And then you need to figure out how you're going to do some measurements to get the answers out. So the very first thing you have to do is even write down this Hamiltonian in terms of qubits. And this isn't totally obvious because it's a fermionic Hamiltonian. It's not a qubit Hamiltonian. So you need to encode it in some way, these fermionic operators in terms of qubits. And what we did in this experiment is use the simplest possible encoding, I guess, which is the so-called Jordan-Wigner transform, which may be familiar to people here. And basically, as I said, we're going to encode n sites of 2 n qubits, 1 qubit for spin up, 1 qubit for spin down. So it's basically saying is there an electron of that form at that site. And this Jordan-Wigner encoding is very nice for 1D systems because the interactions in the Hamiltonian, if it's 1D, map to qubits in some very straightforward way. So the hopping terms that I mentioned in the Hamiltonian, they map to operators for xx plus yy. So that's x tends to x plus y tends to y. So this is acting on a pair of qubits corresponding to the same spin sector but on adjacent sites. Whereas the on-site terms, this is just a projector onto the state 1, 1, and this is acting on a pair of qubits, which is the same site but different spin types or different spin sectors. So the overall Hamiltonian becomes just a sum of some terms which are perform xx plus yy, and some other terms which are perform projector onto 1, 1. So that's the quantum Hamiltonian that we have. Whereas in 2D, this doesn't work quite so well, and basically, I mean, the reason why it's somehow not straightforward to map these fermionic operators to qubits is that you have to take care of fermionic anti-commutation relations somehow. And the way that we do this with this Jordan-Wigner transform is we somehow end up with some Z operators appearing in our encoding. We overlay a 1D line onto the sort of 2D lattice that we have, which I'm showing here for like a 2x4 lattice. And what we get is that if we have hopping terms that are across sites that are adjacent in the line, then they just get XX plus YY as before. But if they're ones which are not adjacent, then we get a string of Zs going sort of along that line. So if we hop between 1, 1 and 1, 2, this corresponds to a terminal Hamiltonian that has a Z operator on 2, 1 and a Z operator on 2, 2. So we now have a terminal Hamiltonian that acts on 4 qubits rather than just 2 qubits, which we don't like because this will give us a more complicated quantum circuit in the end. And in a minute, I'm going to describe how we can kind of deal with that to reduce the complexity.
I have one.
Yeah.
So instead of doing a 2D version, you're just doing a 1D with long range interaction between the fermions.
Well, that's another way of thinking of it. But in the end, like any n by n system, you can map to 1D using the Jordan-Bignow picture. And it also, I mean, it becomes a bit sort of philosophical about, you know, what is 1D and what is not 1D, because as well as it's fair to say that what I've drawn here is just for one spin type as well. I mean, this would just be for spin up, then spin down is kind of the same. And then we have to have interactions between the different spin types, which they kind of look non-local with respect to the Jordan-Bignow picture, but it turns out they don't give you this long string of sets, so you don't care so much about those. But you're right. I mean, one way of thinking about this is you are just mapping to a 1D system. That's right. But it's, I mean, I should also stress that at the moment, I haven't made any assumptions about the way the interactions look on the quantum computer itself. Like the topology of the quantum computer is sort of undefined at this point. Right, so next I want to say something about the method we're actually using to solve this Hamiltonian, and then I'll get on to the sort of quantum circuits and how that looks in a minute. So we're using this variational quantum eigensolve, or VQE method, which is probably very familiar to many people here. And this is optimizing over some family of quantum circuits to find some approximation to the ground state. And we're using a particular sort of ansatz or circuit family here, which is this Hamiltonian variation ansatz, which was developed by the team at Microsoft a while ago now. And the idea here is that we start out in some ground state of some version of the Fermi-Hubbard model. So in fact, this is the non-interacting Fermi-Hubbard model, the one with U equals 0. And that can be efficiently prepared, it turns out. This is classically efficiently solvable. And you also have an efficient quantum circuit for preparing this ground state using these so-called Gibbons rotations. I won't say too much more about this in the talk, but basically, the point is there is an efficient quantum circuit for preparing this ground state with U equals 0. And we're going to start out with that at the beginning of our circuit. And then we're going to have some number of variational steps in our circuit, so some number of layers. And each layer is going to consist of some time evolution operations, where each time evolution operation corresponds to some term in the Fermi-Hubbard Hamiltonian. We're going to time evolve according to that term for some sort of varying times. And these are going to be parameters in the circuit. We're going to try to tweak those parameters to try to find, you know, a good state, so a state that has low energy with respect to the Hamiltonian. And we're going to minimize the energy over these parameters to try and produce the ground state. And okay, so and one reason why one might think this has a chance of working is that if we have arbitrarily many layers, then by the adiabatic theorem, like in fact we know that there exists some circuit of this form that does produce the ground state of this Hamiltonian, but it may take exponentially many layers in principle. Like if we have n sites, we may need exponentially n layers. So what's not obvious in advance is if you can actually do this with a low depth surface.
It's similar to QAOA.
Exactly. Yes, exactly. So it's like a non-commutative QAOA. Okay. And we're using a particularly efficient form of this Hamiltonian variational ansatz. And the sorts of gates that we need for this, there's firstly some gates that do these Gibbons rotations. So I'm not going to say more what these are, but basically these are just 2 qubit operations that can be decomposed easily in terms of elementary gates. We have some gates corresponding to these on-site terms in our circuit. We have gates corresponding to hopping terms. These are going to be time evolution according to these terms. And also we need a few X gates at the beginning. And then, yeah, it turns out that each of these 2 qubit operations here these time evolution ones and these given ones, they can be implemented using two of the gates that are actually on the hardware that we're using, which are called square root of I-swap gates. And also we need some 1 qubit gates, which are kind of free because they're much easier to do. Yeah, and also to say how the parameters work. So these given gates are only used to prepare the initial state, so these don't really have parameters. The other gates, they share a lot of the parameters. So this means, in fact, we don't have many variational parameters to change in our circuit, which helps with the worry that people often have about DQE, which is that it's hard to optimize over these complicated circuits that have many different parameters. In fact, for 1D, for example, we just have 3 parameters per layer of the circuit. Okay, so now finally here's a picture of the circuit, so we can see how this looks. So this is the sort of abstract form, and I'll show you how it looks on the hardware in a minute. But yeah, abstractly, what we have is some part at the beginning that prepares the ground state for u equals 0. Then we have a part that does time evolution according to these on-site terms here. These actually all happen in parallel. I just can't draw them in parallel. Then we have time evolution according to hopping terms. And this, if this is 1D, then we have hopping between site 1 and site 2, and then also between site 2 and site 3. We can't do these at the same time, so we do them in 2 different layers, one after the other. And yeah, so these top 4 qubits are the spin up ones, and then the bottom 4 are spin down. So this would be saying, we want a system that has 2 electrons that are spin up and 2 electrons that are spin down. And then these things here on the right, these form the layers of our circuit. So these things would be 1 layer. And if I wanted to have more, I would just stick them on the end after that. So this part would repeat, and this part with G gates would not repeat. So these things have parameters, which are not shown in this picture, and these are the parameters that the optimizer should try to produce them.
Sorry, the G gates are not repeated.
No, these are not repeated. So these are in a fixed pattern at the start. So at this point, we have prepared the ground state of the u equals 0. And then we do some layers, and then the idea is that as the number of layers increases, we get a better and better approximation of the ground state of the u equals something else. Okay. And I guess the nice thing about this is that you can probably see already, the structure of this quantum circuit is pretty simple. I haven't shown you what happens with these G gates as the size increases. Basically, you have more of them, but you solve a polynomial, many of them, and these things just scale kind of nicely. So this I just showed you was just 1 by n. So things look a bit more complicated for 2 by n, 3 by n, whatever. And I'll say a bit more about that. So, but first, here's how this actually looks on the device. So we're using a 23 qubit quantum processor, and we used up to 16 qubits on there to do our 8 by 1 or 2 by 4 experiments. And the way they're laid out is we have to spin up qubits there, and then we spin down ones down here, in this sort of zigzag pattern. And then, how do we actually do the gate? So what I've shown here on the right is what we would do for each layer of the variational circuit without this initial state preparation part at the beginning. And what we want to do is we want to do some on-site term interaction between the qubits that are on the same site that have different spins. So that's like 1 and 1, 3 and 3, and so on, 2 and 2, and so on. These qubits are not next to each other. So we need to do some sort of swap operations to move them to the right place. So first we do these sort of blue lines, which are swapping 1 and 2, and then we can interact the spin up and spin down qubits from each side. Then we swap them back again, and then we can do the hopping type terms, with each qubit and its neighbors. Then we can do like 1 and 2, 3 and 4, 5, 6, 7, 8. Then we can do 2 and 3, 4, 5, 6, 7. And as you can see already, this is very compact. You haven't used many gates to do this. So things are more complicated for 2 by n. So there's a lot of stuff on this slide now. Basically, for 2 by n, and like m by n is bigger than 1, we do something that helps us deal with these long strings and sets that I previously mentioned. And this is called a Fermi-Hubbard swap network. So what we do is we lay the qubits out in the same way that we would have done for the 1 by n case. We're following this Jordan-Wigner sort of snake that I mentioned before, like this sort of 1D version of this 2D model that we had to begin with. But now, there are some terms we want to do, like, for example, we want to do an interaction between 1, 1 and 1, 2, which are adjacent in this, but they're not adjacent anymore in our line. And to deal with this, we do what's called a fermionic swap operation first. And this basically rearranges the Jordan-Wigner ordering so that now 1, 1 and 1, 2 are adjacent to each other. So we can now interact qubits 1, 1, and 1, 2. And it's important to note this is not the same as a physical swap operation 2, 1, and 2, 2, because it deals with the fermionic anti-symmetry properly in such a way that these annoying Z terms that were being carried around before, they're handled sort of natively. You don't have to worry about them. So what we can do to implement all of these sort of hopping into the vertical operating interactions here is we do a fermionic swap, then we do a then we do an interaction, then we do another fermionic swap, and we do another interaction, and then that gives us all of these sort of vertical type interactions that we had to do there. And the horizontal ones are kind of easier because they're adjacent anyway.
And the fermionic swaps are all done in parallel, right?
Yes, exactly. So throughout this whole approach, we're always trying to minimize the depth. And the nice thing about this method is that you can do all of this stuff in parallel. Yeah.
And Ashley, one more question. In the previous slide, when you were showing the circuit, so here this for the 1D case, right?
Yeah.
Because when you have this in the 2 times n case, then you have this 4-body interaction. Turns out will look more complicated here, I guess, right?
Right. So if I were to show you the 2 by n case abstractly on this slide without this, hardware implementation details on the next slide, what I would have had is have some of these fermionic swaps around these swapping terms here. Well, okay, this is like the horizontal. Let me make sure that's right. Okay. So, right now, okay.
My question was more in the direction of how you would simulate the 4-body interaction terms in the Hamiltonian, right?
Right. Well, okay. So if I had not done the fermionic swaps, then I would have to do these simulation of these 4-body terms. But and so I would have done like something that was like e to the I theta xx plus yy zz or something, and I would have to decompose that operation in terms of gates. But because of whether I take this sort of abstract picture or the concrete one on the next slide, either way I can use these fermionic swaps to get rid of these.
To get rid of the known strings.
Yes. But you actually pay a penalty with this in that it constrains you to do the terms of your Hamiltonian in a particular order. Like if we look at this picture again, we can see that I've had to do 1, 1, 1, 2, 2, 2, and 2, 3, and 1, 3, 1, 4. And then after that, I do 2, 1, 2, 2, 1, 2, 1, 3, 2, 3, 2, 4. So I could not, I would not have been allowed to do this guy and this guy at the same time. So sometimes this might make life worse for me, but it turns out it doesn't make things much worse. Okay, so that's how the quantum circuit looks. The next thing we need to do is sort of optimize over the parameters in this quantum circuit. And this needs some classical optimizer that acts on this parameterized, acts on these parameters. So basically, the idea is now we're thinking in a setting where the classical optimizer just uses the quantum circuit as a black box. And it says, here are some parameters, give me an energy, and then it wants to optimize over the parameters to find a low energy. And in this, what we introduce what we think is a new variational quantum optimizer, which is called Bayesian MGD. So this is a version of a optimizer that was introduced by the team at Friedel called model gradient descent, MGD. But it uses some Bayesian analysis, which is supposed to improve the efficiency of the algorithm. I'm just going to describe this very briefly. And the basic idea is that at any time, we're maintaining a model of the objective function that we're trying to minimize. So the real objective function is a physical thing that we are computing using a quantum computer. We're assuming that locally it's well described by some quadratic function of our parameters, some kind of multivariate quadratic function. But we don't know what the parameters are, right, to start with. Could be anything. And so far, this is the same as the MGD algorithm that the Google team has. And to figure out what those parameters are, we're going to sample the function values. These are energies that we get from the quantum computer. We're going to sample them some random points in some region around where we are at the moment, current input parameters. And we already have some understanding of the model parameters. I mean, maybe not in the first iteration, but after that, we've got some understanding of what the model parameters are. Because probably we haven't moved very much from our previous position, like the parameters. So, and what we can do is we can use this information to update our level of confidence about the current parameters. We can use Bayesian to say, what's our new probability of thinking that the parameters are a certain set of values, given that we previously thought they were something else. And now we've got some new information about them. And so
So that part is maximum likelihood.
yes, basically. Yeah, so we assume that these parameters have some Gaussian distribution. So we have the whole thing has some kind of multivariate Gaussian distribution. And then we do some kind of probabilistic magic to figure out what our best guess is for the new guess. So then this gives us a model for our objective function. And then we just go downhill in that model. We use do some kind of gradient descent step. For some of you who maybe have done physics degrees, this may be useful that you can understand this in terms of a Kalman filter as well, which was news to me when I was looking at this. But basically, this is a sort of algorithm you can use for maybe navigating in some sort of uncertain terrain where you have some sensors that are giving you information about maybe where you are, how far you are away from the ground, or whatever. But they're sort of noisy, and you also have a model for where you are and how far you are away from the ground. And you want to combine these two things together to get a more accurate estimate. Yeah, this is pretty much what we're doing here. We're sort of trying to navigate to the low energy state.
I have a question.
Yeah.
So can you give us an idea experimentally on the order of magnitude of samples needed for this to run properly?
Right. Okay, so there's two questions here. The first is how many points you need, and the second is how many samples at each point. Yeah. And there's a theoretical bound on the number of points you need, and it's basically comparable to the number of parameters of the model. So if you assuming it's a quadratic function, then it grows quadratically in the number of variational parameters that you're optimizing over. And so it's like n choose 2 or something if you have n variational parameters, and you want it to be slightly larger than that because you don't want it to be overly fitting too precisely. And then there's a question how many samples you need at each point, and this it's interesting. It could be as low as like 1,000 samples or something, but 10,000 is kind of comparable. It's sort of comfortable.
Okay, so with 1,000 samples, you don't get any weird things in the gradients.
Well, an experiment, absolutely, you do. I mean, but the hope, but basically, because the algorithm is somehow very tolerant of the fact you have all this noise, it doesn't matter too much. So with 1,000 samples at each point, firstly, I mean, some of them will just be bad for whatever reason. Like at that particular time you ran on the quantum computer, you got some bad result. Other times they'll just be decoherence or something, and they're all experiencing that noise, and that's definitely something which causes you problems. But then you have to, well, to some extent the algorithm corrects for this, but also you need to use error mitigation to correct for it too.
Question following that. So the number of samples actually depends, ideally in general, on the number of energy terms that you're having done, right?
It depends on the number of variational parameters, which in our case is much less than the number of terms. It's like the number of layers of the ansatz.
But what I mean is that in the end of the day, the cost function that you minimize is the Hamiltonian itself, right?
Yes.
And you don't measure each, let's say, so the Hamiltonian is given by a sum of local terms, and you need to estimate all of them, each of them.
Right, but what we plug into the classical optimizer is just the sum of the energies of each of them.
Yeah.
So the parameters that we pass into that the classical algorithm gives us are these variational ones, right? So like there might be three parameters if we're looking at a 1 by n Fermi-Hubbard model that has just one variational layer. And then the classical optimizer expects to get an energy back, which is for each choice of these parameters, which is a number that is produced from the quantum computer by summing up the energies of each of the terms. So the classical optimizer does not know anything about the decomposition in terms of terms. And in fact, I should say that another nice thing about this Fermi-Hubbard model is you can actually measure many of the terms simultaneously, right? Because because they commute. So there's like you can do 1, 2, 3, 4, 5, 6. All of these terms simultaneously.
Okay. I'll ask you more.
Yeah. Okay. Yeah. Tell me when I'm running out of time, by the way.
No, it's fine.
It's great. It's great to have questions, but let me know if I'm.
Thanks. It's going great.
Right. So this really nicely leads on to the next talk, actually, about error mitigation as well, because as we just discussed, if we actually want to get an accurate result, we also need to mitigate the inevitable errors in the device, which are affecting all near-term devices that don't have quantum fault tolerance. And there's a number of different kinds of optimization that we use in these experiments. So firstly, you can use what I call low-level optimizations, which are ones which are sort of specific to the particular hardware we're using, but can be quite effective. Firstly, just choosing a good structure for your quantum circuit is important. And the structure of the circuit that we end up with looks not dissimilar to the quantum supremacy experiments that Google did some years ago. And this is, I think, not a coincidence, and that this sort of structure is particularly good for this device. We need to pick the best qubits that we can on the device. I mean, we're using a lot of the qubits in the device, but not all of them. So we have some freedom in which qubits we pick, and we want to pick the best ones. And also we can use this nice trick called spin echo, where the idea is that our 2 qubit gates in the device, which are all these square root of swap gates, they commute with x tends to x. So that means if we put x on both sides of one of these gates, somehow it should not change the circuit at all. It shouldn't change the unitary that's ultimately implemented. But in practice, it may do because there are errors in the device. And a particular thing we can do with these xx's is that if we have a z error that appears on the device, so let's say there's a sort of e to the I theta z that appears at some point during the circuit that acting on this qubit here. If we do this x, then it sort of changes the direction of that z, and then it can cancel out with the same error occurring later on. So that means that we can actually kind of kill off some of these errors that we see with this, this process, which a number of people have used before. It goes back to AMR, but it's kind of nice to see it does actually work quite well in this device as well. Very simple. There are also some mitigation techniques that are targeted at a particular problem we're solving that we can use. In particular, the Fermi-Hubbard model has a lot of symmetry in it. So firstly, it has time reversal symmetry, and which basically means that if you sort of, the way this is manifested in our setting is that if we choose variational parameters that are the negations of some other ones, then actually the energy should be the same. So if we were to plug in, time evolution according to time minus theta rather than time theta, we should see the same energy. It doesn't change the number of particles. If we time evolve according to the terms of the Fermi-Hubbard Hamiltonian, it doesn't create or annihilate an electron. So if we have a certain number of ones at the beginning of the circuit, then we should have the same number of ones at the end of the circuit when we come to measure. And if we don't, then we know something's gone wrong. We also have some symmetries at the sort of lattice. Like if we have particle Hall symmetry says that if we have n electrons in the system, then if we have twice the number of lattice sites minus n electrons, then we should see basically the same thing up to some overall shift in energy. And also the lattice itself is symmetric, so if we reflect it, then we should see the same answers. And basically, you can take advantage of all of these in slightly different ways, but you can sort of see why this would be helpful to you, because whenever you have this kind of symmetry, you can average over the symmetry, and it can kill off some kind of systematic error that's happening in the circuit. So, in particular, like let's say you have certain choice of the parameters, you can average over that choice of the parameters and its negation, and then you get you might get something which is higher accuracy than if you just did the original parameters.
Actually, one question. So here you have particle number conservation. So I guess the number of spins for the ground state are known depending on system size, so that you input. That's why you input certain ones at the beginning of your circuit. Is that correct?
Right. Well, okay. So this is a good question. So if you're looking for the overall ground state of the whole system, then where you're not restricting particle number, then actually I don't think it is known what the lowest energy is. But I think it's also physically interesting to look at the ground state with a particular number of particles. And in fact, because you don't have so many choices of numbers of particles, you could just search over them if you care about the true overall ground state. So so I mean, basically this is like just another parameter that goes into your circuit. It's like how many spin up electrons and how many spin down electrons. And I think in the literature, people usually actually fix this, and then they look at the physics within that sort of.
Yeah, because for some models, like the XXZ model, like this is known, so that's why I was wondering. Yeah. Right.
Yeah. No, I don't think it's known in this case, but I mean, we'll see. Except for our results, actually, we try all of them. Okay, and the last error-mitigation I want to mention, in a second I'll get on to the actual results, is something called, which we call training with Fermi-Hubbard linear optics. And I mentioned this in a meeting earlier, it goes back to a paper from last year. I'll just, for those who weren't there, I'll say the basic idea is, basically the idea is that if we have some quantum circuit, where every gate in the quantum circuit is time evolution by a quadratic fermionic Hamiltonian, so this is a so-called free fermion system, and these circuits are called fermionic linear optic circuits, FLO circuits. They can be simulated efficiently classically. This goes back to a very nice paper by Helen DiVincenzo, about 20 years ago now. And we can also run circuits of this form on a quantum computer to try and understand better how the noisy energies that we compute on the quantum computer map to exact energies. So if we can do this, then we can apply the inverse of the map between exact noisy energies to some output of the circuit, which is one which is not classically simulable exactly. And we can correct for the noise that we see on the real sort of quantum experiment. So basically, to put this into practice, we find a family, so a whole bunch of these quantum circuits which are efficiently simulable. They should look like the circuit we actually want to run, the quantum circuits that's in our Fermi-Hubbard experiment, and they should be representative of the noise that we see. We run these as sort of training data to get some information about the exact versus noisy energies, and then this lets us invert the noise for the true one. And what we can see if we sort of do this experiment is that we have a nice relationship between noisy and exact energies for these sort of training cases of these FLO circuits. So these are the red points here. So the y-axis is the noisy energy that we would see if we plug in these particular choices of parameters, which give us these FLO circuits. This is the noisy energy that we see in the quantum experiments, and the x-axis is the energy that we should have seen with a perfect quantum computer. And we can see that there's a nice, pretty much linear relationship between the two things. And we can also see that the green one, which is the results that we get out of our quantum experiment, for the actual run, which is trying to produce the actual ground state of the system, we can see that this one also sits nicely on or close to this line as well. So this so one question one might have is whether these exactly simulable things actually well represent the noise that we see in the non-classically simulable one. And it turns out that yes, it is actually not far from the truth. So basically, one thing we do in our error mitigation then is to get this linear fit from the FLO cases, and then use this to correct the errors in this this green point here. This yes.
Is that simulated noise or noise from a real hardware?
This is real hardware. So yeah. So this is all real experiments. And one point you might notice, if you look at this, is that look at what we would have got if we did not do error mitigation. So this noisy energy here that we see from this sort of ground state point, this is bigger than 0. It's I guess 0.5 or something like this. Whereas the true energy is significantly less than 0. So we would not have got a good answer if we did not do error mitigation.
But actually, can I understand it correctly that you can only do this when you can classically simulate all the red points, right?
Yes.
So I mean, you're trapped in this situation where you can only do error mitigation for the classically simulable. I mean, so the point to which you extrapolate is not necessarily classically simulable,
yeah,
but all the others are.
Yes.
Right? So you could simply simulate all of them and then from there predict. So doesn't that make that point also the target point classically simulable?
No. Okay. So the reason I'm able to draw this on this graph is the fact that this is still in the regime that we can simulate, right? So I mean, this is to validate this method works, but there's no reason that for larger sizes we would have to restrict to the case where this green point is one that is classically simulable. All these red ones, yes, that's quite right. They need to still be classically simulable, but and indeed, one thing that you expect to see as you go to larger sizes is that this gap between red and green should get bigger because the classical one should get worse and worse. But and in fact, we have some other experiments where there's quite a big gap, but it's still actually able to do a good thing. But yeah, but I mean, certainly one complaint one might have about this method is it's not clear how well these points should represent the noise, and it's not clear when you put into a simple linear fit. And I think probably more experiments are needed, but I mean, to me, it's already pretty encouraging in a 16-qubit experiment. This basically works. And a key point I should stress here is that doing this sort of simple thing, we're not doing full kind of process tomography or something to actually work out what the noise is. In fact, we don't know anything about the noise. All we know is the way it acts on this energy.
One question. I mean, the plot. I mean, okay. Since the cream point is at the very low. I mean, we basically. I mean, energies become much lower. You're much more susceptible to this linear relationship. So I mean, would it be possible to just think of other not simulatable, add a bit more features to this plot to get other cream crosses along the line in the regime, where also the red crosses are? So I mean, I would find the plot much more convincing if there would be more cream crosses, where you're out of an old regime, up the axis along
right.
the line.
So in this previous paper, actually, we did do this.
Okay.
Yeah. I mean, so that was a much smaller experiment. It was like a 2x1 because that's what we could do on the device. So this was just 2 qubits actually. But so we did do this, and we also did in simulation with simulated depolarizing noise with more points. But yeah, I mean, in this experiment, we were basically caring about how well it worked on the cases that we actually wanted to run it on. But yes, I mean, you're right. I mean, well, I should say as well, we then, I mean, as well as this one test here, which was basically to validate the method, we would use this in all of our results. So, the fact that it did work. So, that there were, okay, so I guess that the number of points, the number of different instances we were looking at it must have been of the order of 30 different instances or something. So it's not perfect for sure, but it's, yeah, it seems to. I should say as well, I think there were some technical optimizations you made to the result, which I'm not going to talk about now, which are in the paper. If anyone wants to look at Appendix C or whatever. Okay, so now we're on to kind of results. And first, I want to say something about how well the algorithm or this method performed, and then say something about the sort of physical results that we could actually get out from the experiment. So first question is, does this P3 approach actually work? Does it converge towards a low energy state? And on the left-hand side of this slide, we've got a graph which is trying to show this. So this main graph is showing precisely, this is the energy, the exact energy achieved by the algorithm after a certain number of iterations at the parameters found by the algorithm, right? So this is not the one reported by the quantum computer. This is the energy that we would get if we evaluated the energy exactly at that point, right? So this sort of tells us how well we are truly sort of proceeding towards the optimal parameters. And I should also say this error here is with respect to the best possible state we can achieve within that variational circuit. This is not with respect to the true ground state, which will be slightly lower. So ultimately, we would expect this error to converge down to 0. And you can see that apart from this middle where it goes a bit the wrong way, it does kind of converge down. And what we can see here in the inset is the reported energy that we get. And I think what's interesting about this is you can see that this does not seem anywhere near as good in the sense that it doesn't really seem to be doing anything very much between the last 5 iterations of this circuit. But you can see that the optimizer, despite getting very noisy energy evaluations, is actually still going in the right direction because the energy is decreasing in both cases. And yeah, I mean, this is just 2 runs, but the same pattern is seen as well. And on the right-hand side, this is showing the effect of error-mitigation. So in fact, I haven't even shown the curve with no error-mitigation. So this blue one is PS, which is post-selection. So this is just if we post-select on the occupation number being right. So that's basically having the right number of particles in the end, which you should somehow always do because you know you've gone wrong if you've got the wrong number of particles. And we can see that the error becomes really very large in some regimes, so especially around this so-called half-filled regime, So this is basically looking at different numbers of electrons along the x-axis, so it's different Hamming weights. The circuit's a bit more complicated around the middle, which is why we expect the error to be bigger. And basically, these other lines are, if you plug in each of these other error mitigation techniques one after the other. I won't go through all of them, but just to note that this last one is the purple one, like this is the sort of final result after we do all of the error mitigation techniques. And we can see that now the error is really pretty good, I would say. And the other nice thing is that we can, they build on top of each other. So, you can apply them one after the other, and in general, they do improve things. Okay. So finally, on to the actual sort of physics, like if you like, so the results that we got out from this experiments. So firstly, I would say that the algorithm we have to show found a good approximation to the best energy that's achievable with the ansatz we were using. So there's two comparators. There's three comparators on that. One is the true energy of the Fermi-Hubbard system of that size. Another is the best we could possibly achieve with a perfect quantum computer. And the third comparator is what we would achieve with some kind of classical ansatz, some kind of variant of this, variant of this system, which is not sort of taking advantage of the quantum effects like quantum entanglement and so on, that might want to use in a quantum computer. And we compare against these different things. So we can see, like in both of these, we've got some different lines. So we've got a blue line, which may actually be quite hard to see, which is the energy achieved by DQE, by our algorithm experimentally. And this, okay, so this, we've got on the x-axis, we've got the occupation number, so number of particles, and we've got the energy, and we can see that it's tracking very closely the simulation. So this is the best possible, perfect quantum computer type what you could achieve with that sort of ansatz. There's still a bit of a gap with the true ground state energy, and that's because we can't produce a perfect approximation of the ground state with this step of ansatz. But importantly, it's far away from this slate determinant line, which is somehow, in thermal systems, this is the equivalent of using a product state as your sort of test state. And this is saying that the quantum algorithm is doing something which somehow goes beyond what we would do by this. So in particular, if we were to use the U=0 ground state as our test state, we would get something which is even worse than this red line here. Okay, and so we see similar results for the 2x4. So it's somehow algorithm finds life hardest around sort of occupation number around 8, which is why I sort of zoomed in there. And in the 1x4 case, we were able to also show that if we go to a higher depth ansatz, so this is the blue line again, then actually it's a very good representation of the ground state. It does better than a depth 1 ansatz. Okay, so this is kind of nice to see. I mean, so the most basic thing you would want from DQE is that it produces very accurate estimates of energies. But what we were really interested in is, could we get any sort of physically meaningful conclusions out of these experiments? And we managed to get a few of these as well. So one particular thing we were interested in is this sort of nice phenomenon that's known about the Fermi-Hubbard model, which is that it should be a metal-insulator. And what this means is it's a system that somehow looks like it should be a conductor, but actually is an insulator in the end because of some effects that are to do with the electronic correlations. And the way that this is manifested in this particular system is that we expect to see that if we have like half of the sites in our system full of electrons, then somehow it's quite painful to have another electron, like you get some kind of energy penalty, because we have this term with this U in front of it, which kind of penalizes you when you have 2 electrons at the same site. So it doesn't want to be in a state where we have 2 electrons at the same site, but somehow when we get half filling, then it's kind of forced to be in this state. And the way that we see this manifested is a jump in the derivative of the energy, so with respect to the occupation number, the number of electrons. So you can sort of see here that as we go along, this is sort of relatively smooth, then there's a bit of a jump at half filling, like occupation number 8. And if we take the second derivative here, which is the inset here, then this is even clearer, that at around 8 electrons, we have this sort of peak here and here, and then it's as much smoother apart from that. we see the same thing in both these different choices of parameters, but U equals 4, U equals 8. We saw something that was less conclusive, I would say, for the 2x4 case as well, but still sort of along the same lines perhaps. So that's it.
One question. Sorry. In the previous slide, well, also this one, I wanted to ask, when you say VQE, I guess are you doing like the full VQE on the quantum hardware, or are you like I mean the optimization runs are all on the quantum?
Yeah, full VQE. We're not doing the we're not doing the thing which I mean I don't want to call it cheating, but it's perfectly respectful thing to do, but not the thing where you like choose the parameters in advance based on
exactly.
That's no. This is doing the full optimization using the Bayes MGT algorithm.
Nice. And the second question is, like what would be the accuracy needed in this sort of calculations, like to provide like meaningful results, like for experimental practical applications?
Right. I think this is a really good question. So I think what I know is looking at some of this comparison of these different classical methods for computing the sort of limiting ground energy of the Fermi-Hubbard model, the sort of level of accuracy that they achieve, like in the sense of the gap between what one of the methods would report and what another method would report is of the order of 10 to the -2 or so. So this is the normalized energy, basically, not normalized by number of sites. So so I guess I would say, like to beat that, we would need the energy to be computed. It's hard to say what to do in the finite size system, but the energy to be computed is like 1% sort of relative error. And for other physically meaningful things, I think it's a little harder to say because sometimes you're actually trying to come up with a kind of qualitative conclusion about is it a conductor or is it an insulator or something. But yeah, I think it's a very interesting question. I don't understand it fully. Right, and then I think this is a good example of these kind of qualitative things, where what we're able to see is this antiferromagnetic behavior, which is saying that the electrons in the system, like their spins somehow should anti-align when they're adjacent. So if we look along a 1D system, then we see that at site I, it's sort of this is the spin correlation at site I, and you see it goes positive, negative, and so on. And this is, I guess, a nice example of something which is qualitatively even to the same conclusion as what we would get from the ground state, but in fact, quantitatively, there are some differences. In fact, you can't really see this, unfortunately, in this slide, but you can. If you were talking about my computer, you would see that there's this sort of nice checkerboard pattern of red and blue in this regime up here and down there as well. Maybe you can see it a little bit more here, but basically we can see that even for long-range pairs of sites that we have this sort of antiferromagnetic. It's stronger as we go to closer.
The observation number.
Sorry?
Is it the observation number?
So
the red and blue.
Oh no. So this is the correlation. So this is the okay. So if this thing's with qubits, it would be like the expectation of. Okay. So this is just the expectation of spin up times. Yeah. So so expectation is easy.
How come we start compare one well, yes, if you compare 1D, so 1 times 8 and 2 times 4.
Yeah.
So you see along diagonal you have these blue spots.
Yeah.
More.
You mean like this?
No, I mean off diagonal. Let me say.
Yeah.
There's a meaning.
Okay, I'm not sure that is actually. Well, okay. No, I think there is some meaning. I mean, part of it is just experimental, precisions, but I think there is a meaning to this, which is that, for example, 1-1 is actually close to 2-1 and also 1-2. So that means so we would somehow. Okay, I mean, I think this is a good point. So 1, is next to 2, 1 in this Jordan-Bigler 1D line, but it's also next to 1, 2 in this. How I got that? Yeah. Okay. No. That was right. So 1, is close to 2, 1, and also 1, 2. So we would expect the correlations between these two things to be sort of stronger, whereas like this site 1 is actually far away from site 4 or something like this. So yeah, I think there is a meaning to this, and this might be even stronger if this was a perfect experiment.
Yeah, no, there is a different correlation factor. So you see, I mean, you have square. So for instance, you compare 1 times 8 up. So you have all these squares. So blue, say red, blue, red. It's repeated everywhere, right?
Right.
Here is more scrambled, right? So it's a different pattern of spin.
Right.
Spin correlation. So I was
Okay. No, that's a good point. Okay. Let's think about that.
But what is the question? I mean, isn't it
No, I mean,
expected that they look different?
you have different spin pattern.
But it's different systems. So I mean, one is a line, and the other one is like a qubit structure. I would expect that there's because I mean the line.
No, I understand.
Ah,
I think I would like to understand a little bit because there is this is purely antiferromagnetic correlation along with this line diagonal, as we say. And the other is not purely antiferromagnetic.
No, I think it's how these axes are written, no? Because it's 1, 1, then it's 2, 1, 2, 1, 2 again.
Yeah.
You see?
It's a relation of the
Yeah.
It's not ordered.
Yeah.
Not ordered the same way. Okay.
I think that's most.
I see.
So indeed, yeah. I mean, sorry, but I mean the reason I did it this way is that basically this one looks nicer if I do it. So but then at the expense of this one, it's a bit more confusing. So. Okay. No. Thank you.
No,
Yeah. So somehow this pattern is less obvious when I see it on my computer actually, because thank you. Okay, and I guess the last result I want to mention is somehow the simplest one, I suppose, which is you can just measure the occupation at each site at the end of the experiment. So the probability of seeing, the number of electrons that you would see if you measured that site. And there's this nice phenomenon you expect to see where if you're in the ground state, you initially expect to have, if you have just one electron in the system, you expect it to be kind of concentrated in the middle. It sort of gets pushed away from the edges. And then as the number of electrons increases, you expect to see some peaks developing that kind of spread out from the middle. And the number of peaks increases as the number of electrons increases. And these are called Friedel oscillations. And we see the same thing in our experiments. Obviously not exactly matching the ground state, but we do see the same phenomenon occurring as well. And yes, this is another physical thing. Okay, so I'm sure I've run out of time, but just to get to my conclusion. So basically, what we were aiming to show is that even if you have quite a low depth quantum circuit, you can still get some kind of qualitative insights into the physics of the Fermi-Hubbard model, even when you're in some regime which is not reproducing the ground state with very high fidelity. What we found in our experiments is that you really need to use a lot of error mitigation techniques quite carefully to get accurate results. A nice thing about our algorithm is that this approach could easily scale up to larger sizes as quantum hardware improves. That was somehow how it was designed. But stress again that everything we did is well within the classically simulable regime. And if we want to get beyond that, we're going to need some improvements in hardware performance, say, or some new ideas. So I think that's everything I wanted to say. Thanks very much to everybody.
Thank you very much, Ashley, for the great presentation. Congratulations on the result, and thank you for the great talk as usual. It was very clear. There were already several questions, but we have a couple more if you don't know.
Sure.
Cool. Yeah, really, thanks a lot. It was very I agree with you. They are very clear and nice. I would be interested in a comparison of what you are doing, or maybe a future perspective, to kind of the first choice to simulate something like this. For instance, I would guess people normally think about, let's say, I take a fermionic atom and I put it into an optical lattice and I simulate the system and everything is there. Could you comment on this? How do you think you can actually win against those systems? Or
that's a very good question. So, okay, so I'm definitely not an expert in those systems, so I'll just say my very high level view. So, I mean, the experiments that are done in some of these systems are incredibly impressive. I would go to very large sizes and see some very interesting effects. I mean, as I understand it, systems like this, they do also experience some challenges, in particular in actually cooling to the ground state, which I think is not always obvious to see what to do. Also, in actually sort of having the control and readout that you might want to get the sort of information that you care about in the experiment. And also, an obvious point is generalizability. So if you have a universal quantum computer, you can do many kinds of simulations. And for example, here, I mean, if we wanted to change to a Fermi-Hubbard model that had some kind of disorder in it or something like that, some different weights on the terms or some local terms or something, that would be really easy to do, but even more complicated simultaneous and to do as well. But yeah, I mean, I agree. I mean, I think these are very interesting competitors. And I would say, if the only thing I thought we could do with the quantum computer was large-scale square lattice Fermi-Hubbard simulations, then I might be a bit scared of competing with them. But I guess I feel that there are enough, even within the world of quantum simulations, there's enough sort of things you can tweak to already make it an interesting challenge for these other systems to try to compete.
Is there any other question?
I feel like this might that major bottleneck is that work not only with the Fermi-Hubbard model but other models is the Jordan control scales linearly, but in practice linearly might not be that good, and so lot of multiple terms. Is there work that they could be doing on like using different transformations or maybe compressing?
Right, that's also a great question. So, in fact, within Prof, but I was not involved with, some people, Joel Klassen and Charles Dublin, they came up with a new fermionic encoding, which I think is the most efficient one known for implementing Fermi-Hubbard, particularly as qubits. So, but there are other encodings as well, like the Stratus-Sirac, Brady-Patayev, which have a much more sort of local form, so they can represent the fermionic system without some operators that scale with the size of the system or something like that. But interestingly, we did a comparison, like in this previous paper I mentioned, where we were looking at classical simulations, and in the sort of very small scale regime, but still, past the boundary of easy classical simulability, like let's say 5 by 5 instances or something like that. In fact, the overheads that you get from these encodings, they seem to kind of outweigh the cost of Jordan-Bigler, actually, because like with Jordan-Bigler, like if you use these swap networks, then you do pay a cost that scales like one dimension of the lattice. So if it's 5 by 5, it will be some constant times by 5, but the constant is not too bad. Like in the case of the surface we're looking at, the constant could be 2, for example. So, already for these small sizes, even though I totally agree it's a major challenge with these very near-term devices, it's still, I think, it makes Jordan-Bigler the most likely candidate for a very near-term experiment. As the system scale sizes get bigger and bigger, you'll want to switch to one of these other encodings. Yeah, I mean, I think it's kind of interesting because it's not clear how much room there is to push any of these other ones down because they need to use ancillas to represent the fermionic system, and so that inherently adds some complexity in terms of the gate cost of actually doing transformations.
Okay, great, that's very clear. Luigi and then Diego, and then perhaps one. Oh, the junior one first. What junior? More junior than you.
Yeah, coming back to this particle conservation and the number of ones that you need to input at the beginning. Because what I saw from the plots, okay, they were just for one system size, but it looked to me like it could be like n halves where you have like the yeah. So let's see. I'm just thinking because so in the XXX model, for instance, the ground state, the global ground state, it has like you have like n qubits, then it n sides, then you have n halves, magnums or ones. I'm not sure if this
that is not actually the ground state. So here, like you know, 8 would be half the length.
Yeah,
which
that's
is
true.
slightly higher than the ground state. And I think this is predicted to continue for large sizes in the database.
Yeah, the thing is, so I'm just thinking about because depending on the number of ones that you have, then the dimension of the subspace spaces like can grow exponentially. And when this is the case, yeah, also like if you use this Hamiltonian variational ansatz, then also like the dimension of the Lie algebra will be exponential, and then you will run into trouble when you scale up. So so yeah, I was just wondering about whether, because here you have like fixed system sizes, so it's not clear how it scales. But even if you have like n thirds or whatever, I mean, it's still like very large subspaces, so there might be problems scaling this down, things up.
Right. So
Even though you're showing like you can have like qualitatively behavior, but still, like if you cannot, like if you run into a barren plateau, you gotta even be able to run that optimization. So I don't know if you
right. So that's just okay. So firstly, I think probably, you know, for things like this, you know, the subspace that you're looking at, probably you want it to be exponentially big, because otherwise I think it's hard, it probably makes life easier for the classical algorithm as well. And I mean, these works, I know you're talking about the algebras and about barren plateaus and so on, and I think I sort of need to understand better how it relates to this and, you know, limitations it might put. But I mean, what I can say is that what we saw from our numerical experiments, which were on larger sizes, is that the number of variational layers you need is somehow not that big before you seem to have quite a good representation of the ground state that you have. I mean, for example, you know, we absolutely are not wanting to spread out to fill the entire space. I mean, we don't want to produce an arbitrary state within this space. We just want to produce, you know, the ground state, right? And also we're doing it with a small number of parameters. I mean, the number of parameters is not growing necessarily with the system size. I mean, in particular, it's growing, yeah, even from our classical experiments before, it sort of seems to grow kind of linearly with the system size rather than exponentially with the system size. So I agree that it's not clear whether barren plateaus, well, at least I don't think it's clear whether barren plateaus would be a problem, and that's something which we need to test experimentally. It's also not clear if it's such a problem if you have this more qualitative picture in mind where you don't want to exactly produce that. So, I mean, yeah, I mean, for me, I don't know, I mean, it's not clear to me yet whether there's any sort of theoretical roadblocks there.
Yeah, because there is this paper by the people, at Los Alamos, they say like, you can look at the dimension of the Lie algebra, and then depending on whether it's exponential or not, after some depth, which I think it's, if I remember correctly, it's linear in system size. So I mean, you don't need to go like to exponentially large depth to run into these issues if you're in a subspace that is like very large. Well, just like I'm just thinking out loud. Yeah.
But I mean, also, I mean, isn't it? It's also related to the way the Lie algebra looks, right? I think like it's. I mean, because you're sort of within an overall subspace, which, you know, could be big or could be small, but then what you're exploring may look different to that. Right? So, yeah. Anyway, I mean, maybe we should.
Perhaps we can discuss those details.
Yeah.
So I suggest that we finish with one last question.
Yeah, I have a general question. Hey, so the question is on on integrable systems. So assume you consider 1D chain. So this is integrable. Okay. But you try to forget about iterativity. You try to implement in the basis you are using. So it's the natural basis. And then you are stuck. After say 2 sides, you are stuck. Then you can't, and then because your problem is transcendental, right? Because you try to solve an equation which is can be largely. Then you discover it's easy to work. Then you make a rotation, and then your system collapses. And you get algebraic, and then you can do much more than say 2 sides. Now, I have 2 questions. First, whether you can say to see any difference between non-integrable and integrable system in between. First question. And second is whether you can implement T2E starting from the correct basis. So you go to the basis that you know that is for integrable system, and then you go back and tangle basically the collected.
Right. So the first question first, I think for the sort of experiments we've done, whether it's classical simulations or ones from the hardware, somehow the only integrable systems we're looking at are these sort of very simple free fermion kind of cases we were looking at for zero. So I mean, we're not trying to produce the ground state that somehow already known. So we haven't like done the test of trying to like effectively learn that circuit that's already known for producing this ground state. I mean, I think it's an interesting experiment, but we haven't done it at least. So I think, yeah, I can't say anything about that. I guess what I can say is that for the particular variational ansatz we were using, it did get harder to produce the ground state as you get away from this integrable regime, right? So we have this sort of U parameter, U equals 0 is exactly solvable. As U increases, it gets harder to solve for the quantum algorithm, but this is not surprising because we're starting in the U equals 0 ground state, and so you'd expect, you know, we're close to 0, it's still relatively efficient. And sorry, I've forgotten the second question.
Yeah, the second question is whether you can imagine to implement.
Oh yes, finding the correct.
Starting from the non-correct basis.
So the question is, if you don't know the basis, can you find the basis, or is it
No?
The question is if you know the basis,
and then you implement the D2E or starting from the correct basis,
right?
which is maybe very far from the basis that work.
Yeah, I mean absolutely. I mean that's I think this is an interesting sort of direction, because somehow what you really want to take advantage of in a quantum computer is everything that's available to you. And if you happen to know an efficient quantum circuit for putting you in the right basis, then I think you should use that first. So, yeah, so no, I think any sort of information you have along those lines, I think it's good to take advantage of in a variational sense. And I don't see how you can't try it.
I guess we must call it a session already. Thank you very much again. This was very, very interesting, very pedagogical, and looking forward for further discussions tomorrow and the day after. Professor Montanaro will stay here with us until Thursday evening. So whoever wants to discuss, may even visit the lab at some point. So he'll be around for a couple more days. So thank you again. Okay.
Thank you.